Good morning. My name is Francesco Celani. I work at the National Institute of Nuclear Physics in Frascati, Italy, and I am membership of a European group called LENR-AHE, devoted to study cold fusion effects, low energy nuclear reaction. The group is made of 15 European partners, one United States, Peter Agestein joined us, and one from Canada. The coordinator is Professor Alexandrov. So this meeting is special for me because I want to honor my close friend Cino Srinivasan. The name Cino is Mahadeva, but for close friend Cino. I meet him this time in Japan, October 1992, during the third conference on cold fusion held in Nagoya, and they give a very strange talk. I read, tritium and HS heat generation during electrolysis of aqueous solution of alkali salts with nickel cathode. The talk was very strange because he used light water instead of heavy water, the time standard, and nickel instead of palladium. So I was very curious about such a talk, and I make my effort to contact him, and he helped me. One girl that was working the conference for 2 organize, and she comes from Tanaka company, palladium, all the research in the world at the time. And I succeeded to meet him. I speak a lot with such girl, and later we marry. So each time I meet again Cino, we start our conversation remembering that day in Nagoya. Nice memory. Okay, my talk is practically a proposal of experiment, and it's the first time I talk just a proposal and not about results of experiments. But this really is really sorry, problem with the computer. Okay, is a unconventional talk because it's based on experiments that we started since 1994. And now we reuse again such technique using constant time instead of palladium that has several advantages but some drawbacks. We use it in short, very high power pulse to induce a non-equilibrium condition. We realized since April 1989 that the non-equilibrium was the key parameter to have some strange effect, thermal or nuclear, in the cold fusion field. So all our activity was devoted to induce non-equilibrium condition. We observed that without non-equilibrium, we never got some interesting results, at least with the accuracy of our apparatus. We are now using a constant time instead of palladium because it is very low cost, about 1,000 less than palladium, and is robust because palladium is easy to break when absorbed hydrogen or deuterium. We used a very strange geometry. Is made like a coil, coaxial coil, and there is at the internal one anode with another wire. This anode a lot of innovative procedure to get non-equilibrium condition. Moreover, we have a kind of a sequential pulsed power supply generation. We make use of intrinsic properties of coil, so electromagnetic effects, to power in situ the counter electrode. And moreover, the surface of wires, constant wires, are coated with low working potential materials that help the emission of electrons, as later discussed. And all the system in the wool is equivalent to the cycle of well-known Otto engine. So we have before increasing temperature, like increasing temperature due to pulse, and at the maximum of temperature, there is a spark of the gas inside the reaction chamber. The low working functional materials was used in electronics since 1920, and also in the beginning of cold fusion effects, so from Professor Panet. We started working with cold fusion continuously since March '89, when we never stopped. In 1994, we introduced the pulsing. So the pulsing has two main effects. First one, electromigration of hydrogen or deuterium absorbed in the bulk of the active material. And moreover, as effect as non-equilibrium, because strong stress to the system. The electromigration was introduced with palladium in 1928 in Germany with the hydrogen palladium. So it's a quite old procedure. And in some aspect, because large voltage along the wire, can remember the coherence effect claimed from Professor Preparata in Italy in 94, 95. So two effects at the same time. The experiment with pulse were a variant of palladium plate using from Professor Tagashi. The results about pulsing was published at the first time in 94, 95, even very famous journal like Physical or Fusion Technology. So it's well stated methods, but we have to stop such procedure because the weak aspect of palladium that make powders event powders after hydrogen absorption. So it's a very, very strong problem. But luckily in 2011, we started a new material, Constantan, made copper nickel alloy, that has lower cost, especially palladium, and moreover is mechanically stronger against hydrogen embrittlement. And it can work up to very high temperature, 900 degrees, important from technological aspect. The constant time absorbed hydrogen starting from 150 Celsius, so very easy procedure to check if the material is good for our operation. And keep up to 700 degrees, at least in our test at the low pressure up to 4 or 5 bars. And it has high resilience, so means it's strong against stress for a very long time. In one experiment, we worked for about 1 year continuously. Usually with the palladium, we can work 1 week, 2 weeks maximum after break. So very large improving. The Constantan give chassis when there are some specific conditions. High temperatures, so means larger than 600 degrees more or less. large thermal gradients along the wire, so it means non-equilibrium. The surface is resonant, means it's like a sponge that is coated with low working function materials. This is a key aspect of our procedure. And there is flux of the deuterium or hydrogen in the bulk or in the surface. So again, non-equilibrium are the key aspects of everything. Other point, we want a non-equilibrium, so we have to add some energy from outside, but this energy has to be as low as possible because we want to get a net balance of energy spent to activate the system and what we can get back. We developed several experimental setup with the Constantan. It's a short review of this picture. At the beginning, just wire, very similar to palladium geometry. Later, we added a counter electrode at very close distance, 1 to 2 millimeters. Later, the counter electrode was powered with DC voltage up to 300 volts to improve Pascal regime. Again, this DC voltage was moved to AC voltage up to 600, and we observed a larger increasing of an Auer effect, external temperature. So recently we decided to increase the frequency, intrinsic frequency of the pulse from 50 Hz up to megahertz equivalent for the rise time, and the voltage from 600 up to 1000. So this is the argument of our talk, and to make the procedure in phase. So when the temperature is higher, we give spark. Before was completely uncorrelated effects. The reactor geometry is a coil. So at the first we give high power longitudinal negative pulse to increase the wire temperature, and at the maximum of the wire temperature while reached, that is spark to ignite in some way the hydrogen or deuterium around. The weak points of procedure can be high frequency problems related. So all the system we have built to have in situ operation of high pulse. The same coil absorb the high power during the pulse generation, and at the end, in times less than 100 nanosecond, produce from himself the fast high voltage pulse. So no effect about impedance matching, capacity effect, and so on. All is simplified. The overheating due to the pulse is quite large. In our typical condition, 160 degrees. And the electromigration effect is very strong, of the order of 2-3 volts centimeter, and so about 4 or 5 times larger than the usual electromigration effects. So all the system has very, very strong non-equilibrium condition. The Richardson effects due to the high power injected means we have a thermonic emission of electrons. And the Pascal regime, it means we have gas breakdown effects. In the experiments using AC excitation, we observed that when there is specific gas breakdown of the voltage. We have larger effect about enormous heat for longer time. So our goal is to make more powerful effects before observed. The geometry of the coil is a little bit complicated. The wire is rounded a lot as iron support. The geometry is like a coaxial wire, but with the main conductor is outside and on inside, and made of constant coilet. The inner is the iron as a counter electrode at a very close distance. Some more details about the construction of the system, and one key rule is made from the insulation that's made by quartz, glass quartz sheet, and is a new kind developed for our purpose from a company. It can stay in France, Italy, France. So they give us free of charge such material. The procedure to get the high temperature is to give a DC to preheat the wire, typically 600 degrees, 500, 600, and alpha give the strong pulse in short time, typically 10 microsecond. So the temperature increases from, example, 600 static up to 700, 800 degrees. The power injected is very large. In some tests, we add up to 13,600 watt, and with the mean value of 11,000 watts, duration 10 microsecond. These tests are made at room temperature, and up to now we don't have degradation of the wires. So the constant is very harsh material. The pulse duration is about, we make tests from 0.5 up to 10 microsecond. The pulsar was developed in 1994 and now was improved to optimize the needed of constant wires. The pulsar is quite flexible, can give up to 200 watt. We need just 220 in our experiments, and with short time duration and power can arrive up to 30 kilohertz of the repetition rate. That is very, very large for capacitor discharge procedure. In our test, we plan to work between 100 Hz up to 1 kilohertz. The termination is very large, I repeat, 2-3 volts centimeter, because the wire is long, 160 centimeter. Extremely large value of electromigration. The procedure to have the extra pulse for the Pascal regime is a little bit original. Usually when the when the coil stops the current, there is extra voltage that is considered deleterious because it can damage the wire itself or the pulsar. But we use the extra voltage, and we collect and send back to the wire to have high voltage to produce the Pascal regime, so the discharge. All this procedure is made in situ with a delay time of only 100 nanoseconds. The drawbacks of such procedure that the high voltage depends completely on the value of the current injected, the formula current over time. So if we have one wire thick, we can have large current, so we can have large voltage. But with a thinner wire, this would be impossible. So we added a new circuitry in order to be more flexible, changing the dimension of the wire. We call this one variable voltage booster. It's a schematic of our system. Is to explain, maybe we need 2 or 3 hours. So I suggest to watch separately. So just the key point is the constant wire put in red with the red colors and counter electrode. Here is a snapshot of the pulse in a typical condition. Where we have 400 volts of the main power. The peak power is about 30,600 watt, and the peak current when the system is interrupted is about 34 ampere. So in this condition, we can have a peak voltage of order 300, 400, not enough for our purpose. So we add another circuitry before the booster to increase the voltage. So in this other snapshot, we have with only 8 ampere peak over 430 volts. The reactor procedure is based on the application of high power and with very tight time control of the extra pulse to have ionization. So in short, Richardson effects. And this, to make a more powerful Richardson effect means electron emission. We call it the wire with the low working function materials. It's a typical Richardson plot in figure 5. And usually the materials, the best material are about 2 electron volts. Now we are starting to reduce the low working infection materials, so it means we can work at a lower temperature for general economy of the system. And we have the counter electrode and the current that can be moved from the surface of the wire depends upon the voltage applied. So as larger as the voltage, as larger the current can be moved. And we need the discharge of the gas. So there is a usual Pascal curve. In the case of hydrogen or deuterium, the curve is made with dots, in this figure. And we have to have larger volt to have some pressure inside. So there is a compromise between the pressure to have a discharge and the total voltage of the system. For particle aspect, we want to limit to 1000 volts. So we mix to the hydrogen or deuterium, argon that have a better performance about discharge. It means at a lower voltage. The speculative sequence of events here are the electrons are emitted from the surface, and at the proper time when they are maximum intensity, they interact with ionized hydrogen or deuterium. This is a sketch, a model, possible model of what happened. We have the Barclay constant, surface covered with low working materials, means electrons can go, and they are accelerated by the high voltage, and these electrons cross with hydrogen, united hydrogen. So all the systems are in phase. This is a key aspect. When there is a maximum effect of one side, Richardson, arrive the spark. So the timing is very, very important, I stress. So one of the nanoseconds of delay is one of the key aspects of our procedure. And we have probably screening effects of due to electrons, the conventional screening effects in nuclear physics, and we have a picometric structure, so altogether help for our go to our direction. And we have, moreover, localized non-equilibrium condition. I spoke before about the Otto-Gene similarity. So we have increasing pressure of air and gasoline, and the maximum of pressure and maximum temperature arrive at the spark. Conclusion about Richardson Pascal procedure are we have experienced before with palladium wires. We were able to get in a quite stable way energy gain between 15 and 30% for several days. And another point, in this experiment, we compare directly hydrogen and deuterium, sequential obviously. But we observe, even with hydrogen, some energy gain, 15%, and with deuterium, 30% in respect to calibration. It was the first time that we observed some anomalous heat with hydrogen. It happened only because pulsed condition. Moreover, in pulsed condition, in specific experiment, we increase the power and we get HS energy up to 250%, but for a short time because the palladium self-destroyed. But it means it will be possible. And it was at a temperature of electrolysis, so means less than 100 degrees. Just a memory about the coil constant is specialized to have non-equilibrium condition along the wires. We have experienced with 50 years excitation and give positive results. But now we can work up to 900 degrees just because constant and not only 100 of palladium. So from technological aspect, it's a big jump. So now all the preliminary tests are almost finished, and we hope from May, June this year to have some nice results. And so in some way we try to have a summary of the experimental setup, easy to understand. And normally the effects happen in deuterium only with hydrogen because non-equilibrium condition. We have the non-equilibrium helped from electron emission from the constant wires coated with a low working function. And these electrons are accelerated from the voltage at the anode, the usual child-Langmuir effects. And moreover, at the maximum at effects, there is a spark. So the hydrogen is not only molecular, but atomic or even ionized. So there is some another possibility for a practical aspect to have only thermionic effects using low working function materials. So this, in principle, this effect can be useful for large quantity of materials, maybe 100 gram, kilogram, so with less effect, but because the cost of material is very, very low, it can be possible without using wire, this little bit sophisticated technology. So I repeat, the materials made, the surface is coated with low working materials, and this kind of approach, so low working is strontium, potassium, iron, and manganese in our specific test. Using low working materials was pioneered from Planet in 1920. So he used the composite materials made of colloidal palladium. So it's a way there are nanoparticles in more ancient terms of asbestos. He make some positive results, and he claimed to have observed transmutation of hydrogen into helium, but their experiments were not reproducible. So later he retracted such observation, but maybe something good happened, even the difficulty at that time. In our case, we make some progress. We have controlled some micrometric nanosized particles, palladium before and now constantan, and we have a direct contact with the low working function materials, means alkaline earth substance in state of asbestos. The use of low working function materials in cold fusion experiment was pioneered from Iwamura since 1998 in electrolytic environments. Low working function materials are usually alkaline earth elements, oxide, calcium oxide, barium, strontium, or alkaline like potassium, cesium. Again, we force the system to high temperature where the electron emission is possible, means practically 700 degrees without excitation. We observe in several tests the chest heat increasing temperature, so toward the effect of low working function, means electrons, and chest heat increasing when the surface of the wire is larger. So to make these wires larger, we just have sponge materials. And again, when we have stimulus, the chest heat increase, so but it's in the previous condition. So just to have a review, we have thermionic cathodes because cathodes are warmed, and this field is common to the industry of catalyzer. There is over 100 years of experience in catalysis field. The thermionic effect, we have substrate of nickel, indeed covered by low working function materials, conventional procedure. And it's remember the well-studied vacuum tube diode on triode. So we have again over 100 years of experience, million of samples produced. So we can use such experience for our purpose. More recently, there are ceramic catalyst elements made of nickel that support low working materials like a mixture of potassium, cesium, barium, calcium, strontium altogether. And this is a industrial product. Typically, they have a basic 70% nickel and used for hydrogenation and other chemical reaction. It's routine work. Conclusion on low working fashion. Constantan was an object of our research, adding layer of low working function material, and the contact has to be as close as possible. So the combination of high surface area with low working function materials is a special favorable condition to have anomaly heat effects. So now we have to thank some companies that help us in these 10 years to survive this very innovative research. The first one is a metallurgical company located in the northeast of Italy. They help us from 2011. They have their own laboratory in LENR field with their own scientists, and we cross-check some of our experiments in their own laboratory or vice versa. And this helps us not only because money that give, but also because psychologically we can be sure that we don't have a big mistake in our experimentation. So it's a cross-check. From some 3-4 years, another company in the Rome area called International Fluid Association give us money mainly to buy some reagent and to pay for the conference abroad. That is quite expensive. We don't have support from 3 years from my institute, so they help us to can speak with our colleagues. So we thank deeply. The special glass sheet was made from CG Favier company, Italy-France company, that developed for us almost free of charge the special sheets made from conventional glass and alumina quartz. So we have to thank deeply them. And recently, the Franco Corradi company in Italy, north of Italy, that has very technological materials, give us very high performance thin alumina tubes that we use for heavy duty test up to 1100 degrees. So we thank really them. And obviously, we are working with the European project LENR-AHE. We have to thank the chair of the project, Korolczewski, in Poland, Szczecin University. And recently, we are collaborating with the group of Professor Bo Oystad at the University of Uppsala in Sweden, and some cross theoretical models changing idea with Anders Kovacs from Broadbit company help us to clarify some innovative point of view. So again, Professor Rayev and collaborators, thanks for the opportunity that I get to can speak to everybody. Bye, and thanks again.